Hello everyone, this is the Kepler's first law tutorial lab. In this lab, the objective is to explore Kepler's first law, which is basically the fact that planets orbit in elliptical motion around the sun, where the sun is not at the center, as you can see here, is at one of the focal points. Now, there are some terms in here that you will probably learn in the lecture, which is the apogee and perigee. We normally call them the aphelion and perihelion for planets. And that's what you will use at the end of the lab. Okay. So most of the lab is very qualitative. In here, you are going to use the simulator. And if you leave it as it is, you can include the axis and semi-axis, so your A and B. We call this the semi-major, semi-minor axis. And then we can find the value of C, which we use to find the eccentricity. C over A is eccentricity. So you're going to do that of the lab. Now, if you click on here, you will have a planet orbiting the sun. And then you can see how it slows down as it's farther from the sun, and it speeds up as it gets closer to it. All right. We studied that in orbits, in gravitation, and that's how Kepler and subsequently Newton realized that the trajectory of planets around the sun was an ellipse that allow us to explain facts or observations such as Mars retrograde motion, right? And the fact that planets orbit at different rates and at different periods around the sun, like Mercury, Venus, the Earth, and Mars. So the first questions are more about what you can observe, like what you can do, like some actions here. And some suggested actions is by making it closer, pushing it farther, pulling it farther, and see what happens with the planet as it orbits the sun. Like as you make it more circular. And how do you make it more circular? As you make the sun be more at the center there. Right? So instead of having semi-major or semi-minor axis, you have a well there, right? You have a radius. All right. Now, the effect on the orbit shape and size. You can see what happens as you click the simulation, as you play the simulation. You notice that there is not much of a change in the orbital period. So that's something you can comment about it. Now, I would suggest in the sketch, just print the screen. Just do this. And actually, maybe that's not very good. Let's move myself outside. Do this again. You can just copy this. And then you go to the file, and then the sketch can be just that. Right? And then you can just discuss. If you cannot complete 4 actions, at least do 3. All right, I have 4 suggested here. It's very, as I said, more observational than anything. And then you can answer these questions. What do all orbits have in common? I mean, guys, at least for the planets, you can see, right, what's the main characteristic, right? The sun is never at the center unless you make it circular. But that's not always the case, right? You start like that. You can add the grid, the axis, the focal points, and then you see that, right? Describes 2 ways to reach the edge. That's basically extreme cases where you cannot, for example, one of them is this. You have a warning there. That is basically what that question is asking you, okay? So there is one case that is very close. You can figure it out what happens for the second case, right? What's the second case? Now, for the eccentricity, where will the other focus be relative to the sun? So that you can just activate the focal point and then you can see. right? This is a center here. That's a focal point. This distance here, guys, by the way, from the sun to the center is called the C value, ABC, okay? That's what we know. That's what you probably have read about, like focal distance. It's kind of similar, all right? Where is the center of the ellipse located as measured from the sun? Basically, question one. What is the measure of the semi-major? Okay, so how do you measure the semi-major axis? Because you need that for the eccentricity. So let's show you how to calculate eccentricities, all right? And everybody is gonna have a different answer for this. I'm gonna use that, all right? Let's get this out of the way. Use the measuring tape. And your semi-major axis is from the center to here. All right, that's the largest distance. So you can open a notepad and you can write the value of A equals to 1.39 AUs. And then the value of B (1.30). And if you look closely here, the difference is 0.01 AUs. That's okay. Let's use the values I measured. All right. How do you find C? Well, C squared equals to A squared minus B squared. So C squared equals to 1.39 squared minus 1.30 squared. So C squared equals to, so we open the calculator, 1.39 plus 1.39 plus 1.93 minus 1.3 plus 1.3, 1.69. C squared equals to 0.30 or 0.936, 0.26, right? Yeah, or 0.24. Oh, yeah. So, okay, and then C is the square root of that, 0.49 AUs. So the eccentricity is C over A, which is 0.49 over 1.39. I'm just showing you this so you can see how everything works out. 0.35. If I look at the table, 0.36. So not bad, not bad, right? That's basically the eccentricity of this object around the sun. Okay, so not very elliptical, but fair enough, right? It's in a value that we consider to be elliptical, all right? The Earth is almost circular. The eccentricity of the Earth is almost zero. There's still a difference between what we know as the aphelion and perihelion, but not enough to be considered highly elliptical, all right? Which, by the way, explains why it was so hard for physicists and astronomers hundreds of years ago to figure or to realize that planets orbit in elliptical fashion. So then you can click on the eccentricity like I show you. What does eccentricity mean in your own words? I kind of already mentioned or say that. How does eccentricity affect the period of the orbit? So for that, you want to, and you can make this fast, you have a 0.36, 0.35 eccentricity there, and then let's change this. Let's make it more eccentric, more, you know, and then you can even use a stopwatch to see how long it takes, and then, right? You can use that, and then you can even make it less. You have to be careful with this because you make it bigger. All right, there. And then, so that's basically what you have to do. Just comment about what you notice about the orbits when you change the intensity. discover how to create a circular orbit, guys. Just do it here. Circular orbit, and then that's a shortcut. All right, instead of playing with this, just do circular. That's easy. There. Okay, this table here. So in this table, you're gonna do Mercury, Venus, the Earth, Mars, and Jupiter. And I want you to pay attention here because you are gonna find the measurements of the aphelion and perihelion. The aphelion is the largest distance from a planet to the sun, and the perihelion is the shortest distance, the shortest approach, okay? And you can use them to find the focal distance and the eccentricity, right? These equations are equations that we can prove in physics, right? So let's see, for that, let's go and let's reset this. Let's go to Mercury, that's the orbit of Mercury, and then let's use the grid. So as you can see, you cannot see the center here. So how do you find your A and B? You can't. But you can find, what you can do is you can measure the aphelion and perihelion. So the aphelion, the aphelion will be this. About 0.47 AUs. So let's go here. And the perihelion will be 0.32 AUs, not bad. Right, so there's a difference there, 0.15 AUs. So let's find the eccentricity. Is the aphelion minus the perihelion over the aphelion plus the perihelion. So 0.15 over 0.79. All right. So let's see what I get. All right, 0.19. You can even round it to 0.2. All right. So we can find the aphelion, perihelion, right? That's what you write here. See, whatever. Oh yeah, aphelion minus the value of C will be 0.075, if you think about it, right? Because this minus this divided by 2 is that, and then you see we got 0.20. Now, I can Google eccentricity of Mercury. And it's about 0.205. Not bad. Not bad, guys, right? Like with a simulator, you can identify. There's a level of uncertainty, of course, which is okay. And that's what you have to answer in this question, all right? That's what you have to do for this table. So it's a very fun lab, guys. It's very interesting. This is basically the file that you're gonna find in Blackboard. So make sure that if you have any questions, please let me know. Okay, via a message or an email. Other than that, guys, have a nice rest of your day. Take care.